we will discuss the equilibria involving ions. It is well-known fact that the aqueous solution of sugar does not conduct electricity, but when common salt is added to water, it conducts electricity. Conductance of electricity increases with an increase in the concentration of common salt. On the basis of conductivity, Michael Faraday classified the substances into two categories. One is electrolyte and another is non-electrolyte. The substances conduct electricity in their aqueous solution are called electrolytes, while the other do not conduct electricity are called non-electrolytes. Michael Faraday further classified electrolytes into strong electrolyte and weak electrolytes. Strong electrolytes on dissolution in water are completely ionized, while weak electrolytes are only partially dissociated. Here you can see the example of an aqueous solution of sodium chloride is dissociated into sodium ions and chloride ions, while that of acetic acid mainly contains unionized acetic acid molecule and only some associate ions and hydronium ions. There is almost 100% ionization is observed in sodium chloride as compared to less than 5% of ionization of weak acid or acetic acid is observed. In weak electrolytes, equilibrium is established between ions and the unionized molecules. And this type of equilibrium involving in ions in aqueous solution is called ionic equilibrium. Ionic equilibrium is the equilibrium established between the unionized molecules and the ions in a solution of weak electrolytes. Because strong electrolytes dissociates completely. Acids, bases and salts come under the category of electrolytes. In 1899, Arrhenius discussed the temperature dependence of reaction rates on the basis of an equation now usually known as Arrhenius equation, and he was the first to discuss the greenhouse effect called by the name. Arrhenius received Nobel Prize in Chemistry in 1903 for his theory of electrolytic dissociation and its use in the development of chemistry. According to Arrhenius' theory, acids are the substances that dissociates in water to give hydrogen ion, and bases are the substances that produce OH ion or hydroxyl ion. For example, HCl, HNO3, H2SO4, H3PO4, HI. These are called Arrhenius acid because it furnishes hydrogen ion. Hydrogen ion in water is extremely hydrated and high charge density. Acids are classified as monobasic acid, dibasic acid, tribasic acid. Monobasic acids give single hydrogen ion. General example, Ha. Whereas dibasic acid gives 2 hydrogen ion per molecule. A general example of dibasic is H2A. And tribasic acid gives 3 hydrogen ion per molecule. HCl, hydrochloric acid, HNO3 are the example of monobasic acids. Sulfuric acid is the example of dibasic acid, and S3PO4 is the example of tribasic acid. Any substances that release hydrogen ion as only positive ion in the aqueous solution is called Arrhenius acid. And here you can see the picture of hydrogen chloride plus water. It produces hydronium ion and chloride ion. In simple way, we can say that when aqueous solution of hydrogen chloride furnishes hydrogen ion and chloride ion, it is classified as acid because it forms hydrogen ion, whereas sodium hydroxide is base and aqueous solution of NaOH provides sodium ion and OH ion. Arrhenius base is a compound that increases the OH ion in aqueous solution, and base is classified as monoacidic base, diacidic base and triacidic base. Monoacidic base gives single OH ion per molecule. Diacidic base gives 2 OH ion per molecule, and triacidic base gives 3 OH ion per molecule. Ammonium hydroxide and sodium hydroxides are example of monoacidic base. Barium hydroxide, calcium hydroxide, these are the example of diacidic base. And ferric hydroxide is the example of triacidic base. Now, Bronsted-Lowry concept. Actually, it is the acid-base relationship. The Danish chemist Bronsted and English chemist Thomas M. Lowry gave the more general definition of acid and bases. And according to Bronsted-Lowry theory, acid is a substance which donate hydrogen ion are called Bronsted-Lowry acid, whereas bases are the substance which accept hydrogen ion. That means acids are hydrogen ion donor, whereas base is hydrogen ion acceptor. For example, hydrogen chloride, when hydrogen chloride acts as acid and water acts as base. Hydrogen chloride donates a proton to water molecule which acts as base. And we observe here that water acts as base. Water acts as base because it accepts the proton, and the species hydronium ion is produced when water accepts a proton from HCl. Adds proton, water, and HCl is the conjugate acid. It produces chloride ion, that is the conjugate base of HCl. And similarly, water is a conjugate base of H3 hydronium ion, and hydronium ion is a conjugate acid of base water. Another example of conjugate acid base pair is NH3 plus HCl. NH3 acts as Bronsted-Lowry base and HCl is Bronsted-Lowry acid. And NH4 ion is conjugate acid of base NH3, and chloride ion is the conjugate base of acid HCl. The acid base pair that differs only by one proton is called conjugate acid base pair. A strong acid will have weak conjugate base. Reaction will always proceed from strong acid or from strong base to weak base. And another example of acid base pair is NH3 plus H2O. It forms ammonium ion and OH ion. Ammonia adds one protons. That means ammonia, that is base, and it forms conjugate acid. In another word, we can say that ammonium ion, that is the conjugate acid of ammonia, that is Bronsted-Lowry base. Conjugate ammonium is conjugate acid, and water is acid, acts as acids, and it loses proton and forms OH ion, that is conjugate base. Conjugate base. In 1923, G.N. Lewis defined an acid is a species which accepts electron pair and base which donates an electron pair. Base have lone pair also. Electron deficient species are considered or acts as Lewis acid, whereas the species like water, ammonia, OH, which can donate a pair of electrons, can act as Lewis base. That's all for today. In next video, we will discuss about ionization of acids and bases.